Okay, all right, good job, Sarah. All right, so do you have any questions for me before we start?
All right, while we wait to start, go to Blackboard and download the Zmax file for today. It's not working. There it goes. All right, let's see how many people we've got here. We've got 14. I'll wait another minute or two. And meantime, go into Blackboard for those who just got here and download the Zmax file for today.
Dr. Small, I had a quick question on the problem set that was due.
Yeah.
So for number 7, when we were figuring out what combination of lenses would work in order to widen the laser, my thought process was, okay, we can put a diverging lens in front and then a convex lens right after to parallelize, if that's a word, to make the rays parallel that were diverged. Is that wrong or is that correct?
It's called collimate. And not only is it correct, it's what I actually discussed in class a few weeks ago.
Okay, that's what I thought, but I was studying with someone and he said it was the other way around. And I was like, no, that makes the rays, that focuses the rays more.
So the basic idea is to do this, and then we're just assuming that the rays seem like they're diverging from a point back here. So this would be minus F1, and this would be F2. And we did that in class a few weeks ago, and it's exactly correct. And you need to start placing less stock in what someone else tells you and more stock in what you actually remember from class. So
yeah, I have trouble with that.
There's this thing in social science called the Condorcet jury theorem. And the idea of the Condorcet jury theorem is that if you poll a large number of people on a question, then you will, as long as everybody has some information, they might just be guessing, but as long as they have some amount of accurate information, all of their guesses will be ever so slightly biased towards the right answer. Now you might say, well, what if they got biases towards various wrong answers? Sure, but the whole idea is that all of them, they have to have uncorrelated biases. They've all got their own weird idiosyncrasies, okay? But everybody's got a different idiosyncrasy. That's the whole definition of an idiosyncrasy. And if you do that, if that's the case, then you can get an accurate answer just by polling a large number of people and averaging their answers. And this actually works in some cases. There's the famous example of having people guess how many marbles are in a jar or whatever. there's apparently surveys can work amazingly well, asking people to average their guesses about like the height of the Empire State Building or something without anyone looking it up. We know that there are prediction markets. I mean, in some sense, markets are predictors. You know, if you take out a futures contract right now to buy a bushel of wheat in November after the harvest, you're making a prediction about a whole bunch of things, including a prediction of the weather between now and November that will affect whether that wheat grows well or not. And actually, the worse the weather, the more expensive the wheat will be. So, you know, if you predict a low price, you're betting on good weather. Now, you might say, how could any individual really know the weather? Well, apparently they don't, but somehow these futures markets are incredibly good at predicting future prices, not perfectly. So you think, okay, the Condorcet jury theorem works. But then I repeatedly hear stories of people coming to me and telling me that they were talked out of the correct answer by a classmate. You get a bunch of people together and somehow the wrong answer prevails. And in unrelated news, we in California believe that most matters should be decided by a ballot measure where you have the people vote on complex policy issues that they haven't studied up on. And, you know, we just trust that this works. Anyway, any other question?
I
Yeah.
got a question. I was the student that led Juan in the wrong direction.
Okay.
Well, no, he didn't lead me direction. I ended up writing down my answer.
Okay.
But anyways, it still works the other way though too. If you were to have the convex lens first and then the diverging lens second, you would achieve the same results, correct?
If we had, yes, it would narrow the beam. It would absolutely narrow the beam. If we were to widen, could we widen the beam that way? I mean, the problem is if we tried to widen the beam, you want to widen the beam with a small lens. And the problem is that if we're trying to widen the beam, we start off with a narrow beam. So it's going to do this. I mean, I guess.
But now you need a convex, right, to converge.
Yeah, so you could certainly do that. It's not as good as the
That's
top one.
Galilean, right?
Yeah, but it wouldn't be as good as the top one. Spencer, what was your idea for widening the beam by starting?
I misunderstood the problem. I think I forgot that the point of it was to expand the beam rather than I was focusing more on the parallelization of the rays. So.
Yeah. Oh yeah, if you just want to collimate to a
Yeah.
different diameter, you're absolutely right. We can do this.
Yeah, but yeah, I forgot to widen it, which that makes a lot more sense.
Okay. Okay. By the way, modern education is premised on group work. Modern education, everyone tells me that what you need is you need to have a group of people together talking, and then the right answer will come out. As opposed to having me talk, I will never say the right answer, apparently. So, you know. Anyway, no, I mean, you're absolutely right. It can converge. It can collimate the beams to a different diameter. It just can't collimate to a wider diameter, because if we were to put a some sort of diverging lens here, then it could only take them like that. That's the problem. All right, so we're going to talk now about aberrations. We're going to talk about the fact that lenses are imperfect. And I'm going to start with an argument that is based on light collection theory, since we just did a bunch of light collection. So let's say we have a little object and it has radius, or we'll call it say it's y above and below the axis. So then if it is coming out of the page like this, y that way, I'll just say it's like this. This is y. Its area is y squared, and we'll call it y1 because it's the object. And we could ask, what is the flux of light onto this lens? And so we would be adding up over all of the angles. And we'll say that y is really tiny. So that if I look at this ray and this ray going parallel to each other, or going to the same point, these two rays are practically going to the same point, okay? They're so tiny that in terms of the range of angles that we look at when things are hitting the lens, technically, we should take into account the fact that if I've got a little object here, a ray that is, say, doing this and this is a different range of angles than these two rays. Okay, those are, strictly speaking, different ranges of angles. But we're going to assume that the thing is so small that we can neglect that effect. So the flux of light onto the lens is the integral from 0 to alpha 1, the acceptance angle on the left side, of sine theta d phi. And then there's also a factor of cosine theta, which I should have really written there, but that's a detail. And then there's an integral from 0 to 2 pi to integrate over phi. And so we are left with sine theta, the integral of sine theta 2 pi cosine theta d cosine theta. Now, I'm skipping too many steps. That's a bad thing. Sorry. We are left with 2 pi times the integral from 0 to alpha of cosine theta sine theta d theta, which is equal to, among other things, 2 pi sine squared alpha over 2, because we've got sine theta multiplied by its derivative. Whenever you've got, that's the derivative of sine squared theta. All right, so that's the fraction of light that we should be getting. Now, on the other side, all right, so that's the fraction of light. I wrote it slightly differently, but that's the flux of light onto this surface. Sorry, that's the flux of light onto this surface. Am I making a mistake? Let me just, there's something that's bothering me in the back of my mind, and I'm checking something right now. Sine theta comes from the range of angles that we consider. The cosine theta comes from the flux. Yeah, we're fine. Now, in order to figure out how much light we get, though, we have to multiply by the area. The more area that we have producing light, the more light we emit. So we've got pi y1 squared sine squared alpha 1. And that, if we were to do the same calculation on the other side, should be equal to pi y2 squared sine squared alpha 2. Cancel some pi's, and we can take some square roots. We're left with y1 sine alpha 1 equals y2 sine alpha 2. So if we just view this as a matter of counting up rays, then everything should be good as long as this condition is satisfied. And this condition turns out to have a name, the Abbey sign condition, named after Ernst Abbey. But there's a little bit of a problem here. Y2 and Y1 are in here. Those two are related to the magnification. And now let's just look at this lens and the magnification issue a little more carefully. All right, if we were to calculate, here's alpha 1, here's S1, here's alpha 2, here's S2, here's the radius of the lens. Tan alpha 1 is equal to R over S1. Tan alpha 2 is R over S2. And when we put all of that together, R is equal to S1 tan alpha 1. It's also equal to S2 tan alpha 2. So I could say, I could use one more fact, which is that S2 is equal to the magnification times Y1, which is equal to Y2 over Y1 times Y1, but it's also equal to S2 over S1. Sorry, the magnification times S1. Right? So I get S1 tan alpha 1 equals Y2 over Y1 S1 tan alpha 2. Cancel some S1s. I'm left, then I multiply both sides by Y1. I'm left with Y1 tan alpha 1 equals Y2 tan alpha 2. So if all I'm doing is counting up paths, then I seem to have a problem. Because on the one hand, I've got this condition with the tangents. The only way these can both be satisfied is if the angles are very small. Now, this doesn't mean that really good lenses don't exist. All right. I made this key assumption that the ray on this side is going to hit the lens at the same height that the ray comes out on this side. And real lens systems are never just real good lens systems. The kind of lens systems that deliver high quality imaging are never just one lens. there's always a whole bunch of lenses, and rays are going up and down and changing angles and positions repeatedly. And so in those types of systems, the fact that a ray comes in at this height means very, very little. Right? It comes in at this height, it goes out at that height. And this final S2, or S final, or whatever, it is entirely possible to satisfy the kinds of conditions that we need to satisfy. But this is just a hint that we're already running into problems. We're running into some inconsistencies when we develop a theory of thin lenses. Now there is another problem, which I'm going to switch to some slides for. All right. So there's something called spherical aberration, which you've already seen evidence of. What we've got here is imaging of a point object under different conditions. And the basic problem is that in the first week of class, we derived the idea that an ideal lens should either be a Cartesian oval or it should be a hyperbola, depending on the situation. If we're imaging to infinity, it's a hyperbola. If we're imaging from one finite distance to another finite distance, it's a Cartesian oval. Well, here I've drawn an aspherical surface and a spherical surface. And at first they match up very, very closely. But as you get farther and farther away from the axis, we see that they start to differ from each other, okay? And one way that they differ is that whereas this ray that I've drawn here, if we had the ideal aspherical surface, it would have hit it right where my cursor, right where my mouse is, and then been deflected. Instead, it goes farther out, hits it at a more extreme angle. And when it hits it at a more extreme angle, what happens is that it gets deflected through a more extreme angle. Any questions on that argument? You've seen this every time you've played around in ZMAX. Here I have a lens that has been, well, sort of optimized for 1 to 2 imaging, meaning that this distance on the left is half of the distance on the right. Let's change the aperture value. When we change the aperture value, change the entrance pupil diameter, the width of the lens, what we find is that some of the rays the outermost rays are getting deflected at steeper angles, okay? None of the inner rays have actually changed. There's nothing wrong with the inner rays. It's not like the inner rays did anything different from before. It's just that we have more rays. And so the way it's drawing it, we're seeing the effects of the outer rays. If you look over here, if you zoom in, you see that indeed some of the rays get focused there. The rays a little bit farther out get focused maybe here. The rays a little bit farther out get focused or come to their narrowest point there, okay? So different rays are actually getting focused at different positions along the axis. Some of them are coming to a focus right here, actually. Some of them are coming to a focus right here. And if we were to include more rays in the diagram, we would see more places where things come to a focus. Any questions so far? This is called spherical aberration. And it's called spherical aberration because it was noticed and the theory was developed with spherical lenses. But in fact, it's an aberration that happens anytime you have something that isn't the ideal Cartesian oval for that situation. Whatever the ideal lens is for that situation, if you deviate from that shape in any way, then you will get this spherical aberration.
I have a question.
Sure.
So I know you mentioned how spherical lenses are typically easier to manufacture.
Uh-huh.
So, I'm sorry, I'm trying to figure out how to word this. So I'm guessing it would be favorable to like make that perfect sphere and, you know, get the imperfections of spherical aberrations versus attempting to make a nice oval lens? Or is it just like cost? It's just really expensive to do them. They're doable, it's just expensive.
Yeah, it's expensive to make a perfect sphere.
The nice Cartesian oval.
Well, nowadays, in principle, nowadays you could make a Cartesian oval. Nowadays, with the kinds of tools that are available, you could make a pretty good Cartesian oval. Now, of course, there is no such any realistic object will have surface imperfections. But the things that people are able to do with diamond turning and stuff, I'm not up on the details, but I've seen presentations by them. You can pretty much specify a surface and they make it to pretty high precision. The thing is that this is new technology. It's very custom, one at a time work. And also you're working with polymers instead of glass. And polymers have their own drawbacks. Polymer is a fancy word for anything made out of long chain molecules. You are made of polymers. Most of your, well, 70% of you is water. The other 30% of you is mostly polymers. Any long chain-like molecule is a polymer. Rubber is a polymer. Plastic is a polymer. Paper, cellulose is polymers. Sugar isn't really a polymer, but polysaccharides, complex carbohydrates, starches, those would be polymers. Lots of things are polymers. DNA is a polymer. Proteins are polymers. Polystyrene, styrofoam is a polymer. And you can make transparent polymers. There are plenty of transparent plastics. The problem with them is that sometimes they have much worse dispersion than glass, sometimes not. They're not as physically sturdy. And they tend to be very bad if you want to work with polarized light. If you care about the polarization of light, polymer optics could be terrible. If you don't care about polarization, then nowadays polymer optics could be good. The materials themselves, I mean, plastic is cheap, but you know, any kind of custom manufacturing process is going to be expensive. All of these things are getting cheaper. So anything I say today might not apply in the future.
Do spherical aberrations, does the deviation, the distance from the normal focal point, does that depend upon the index of refraction of the material too, in addition to the geometry?
Oh, yeah, absolutely, yeah. The amount of deflection depends on the angle it's coming in at, and it depends on the refractive index, definitely. Now, if you work with a higher refractive index, on the one hand, that could lead to more deflection, but on the other hand, you're using a less curved surface. So it can be a complicated trade-off. Now, most lenses are still spherical. And keep in mind that also there's just another reason why people still avoid A-spheres, besides the fact that A-spheres are more expensive in many cases, or at least an A-sphere made out of the kind of material you want might be more expensive, is that there are just centuries upon centuries of knowledge base built up around spherical glass. And you just don't toss that out overnight. not when you need things that are reliable. If you want things that are new, of course, you're working beyond those centuries of experience. But when you want things that are reliable, you go with things that people have been making for a very long time. Now, when we say that spherical aberration exists and it's a problem, that doesn't mean that all spherical aberrations are equally bad. Let's take this back to that case. And let's do a quick adjust. It should still be optimized for that. Oh, no. Okay. Well, now let's flip this lens. And it might not be obvious that the spot size is worse. So let's put in a spot diagram. Let's just for now look at the on axis. We'll worry about the off axis later. We'll tile all windows. Okay. So the spot size for the on axis, RMS radius 118 microns. Versus 31 microns. So saying that spherical aberration inevitably exists does not mean that all spherical aberrations are equally bad. Let's look at an intermediate case. Let's look at a biconvex lens. So let's make this about 7. You're going to see why I'm going to make it about 7 rather than exactly what it should be. I'm going to make this surface be equal to this radius. I'm going to make this radius of curvature equal to the previous radius of curvature multiplied by -1. All right. And then I'm going to do a quick adjust. And we get that. And that's even better. Now, everything that I just made here was with spherical surfaces, but some of them were better than others, and some of them were worse than others. Any questions so far? There's a basic rule about aberrations, which is that aberrations get worse as n sine theta gets worse, as n sine theta gets bigger. So if we think about the Plano convex lenses that we were working with there, I'm going to switch to drawing again. So if we think about Plano convex lenses, this was a problem on the homework, and I wanted you to think it through for today. I can make that more straight than this. This case versus this case. In both of these situations, they hit the surface at the same angle, all right? But in one of these cases, so we have the same theta in both situations. We have a different n sine theta. So we are going to get different deflections. Now, some people were worried by that. They thought, well, the theory we've been doing suggests that these two orientations should have the same focal length. In truth, they have almost exactly the same focal length. Within the theory we're doing, they have exactly the same. But still, it was worrisome to some people. We had to discuss that in office hours. Here's why these two lenses behave quite similarly, even though the deflections are different in the two cases. In the blue case, we get a very large deflection there. In the red case, we get a smaller deflection, but then we get a second deflection. All right? We do not get, we get a second deflection there. All right, so we get two deflections. And the sum of those two deflections, if we were to go through it in painstaking detail, would be almost the same. But not quite exactly the same. And whenever you work with larger angles, you wind up having more problems with aberrations. Aberration just being a word for things going wrong. Any questions so far? So if you take nothing else away from this so far, you should take away that when you send rays, if you have rays coming parallel to the optic axis, you do not want them to hit a Plano convex lens on its flat side. In general, a bunch of small deflections is better. And I have a slide for that in my other device. So hang on a second. Let me share this screen. We'll go back to it. This is a very, very good and very expensive lens system that someone designed for lithography. And that is an insane number of lenses. It must have taken many, many hours of a very expensive lens designer's time to design that, and many, many hours of some very skilled technicians' time to make sure that that system is indeed aligned. But what you should notice is that at each surface, the individual deflections are quite small. Each ray just barely changes direction at each surface. Of course, they change direction, but not by much. And so when you watch these rays traveling through here, they just barely deflect. They almost look like a smooth curve. Of course, it's not. Of course, it's really choppy. But doesn't it almost look like a smooth curve? That's what they're going for, very tiny deflections. Any questions? So
what if you could just have,
yeah.
Never mind.
No, ask it.
It's insane.
Go ahead.
What if you just had one solid piece of glass, but the index of refraction changed dynamically as you varied position, so that you wouldn't need an ensemble of lenses, but when
solid. That exists. It's called a GRIN lens, graded index lens. GRIN lenses exist. Of course, you know, they have their own drawbacks. They're expensive, they're large, but, you know, and I'm not an expert on where they're used, but I know they are used.
Cool. I'll have to read more on that. That was a unplanned thought.
No, GRIN lenses exist. Yeah, so once upon a time, people taught aberration theory in great technical detail. And I'm going to give you a tiny taste of it so you know why they use words like third order aberration theory. But the truth is that you still, if you want to become a lens designer, you still learn some of that theory, but you also learn a lot of rules of thumb. I mean, what probably happened is that someone had a bunch of rules of thumb and intuitive ideas that they used to say, okay, well, we better have sequence of positive, negative lens, then some positive, then some negative, and they had a bunch of ideas in mind. And then they fed this to a computer and they said to the computer, optimize it. And the computer tried many, many, many configurations before finally optimizing it. So people still learn aberration theory, but people also learn the basic principles. And then they know that when they actually design the lens, they might do some hand calculations to estimate, okay, well, I want something with roughly this curvature here and roughly that curvature there. But then they give it to Zemax to just run through and do all of the trial and error to see which curvature actually works best. And the basic idea to take away here is that all of the deflections are very, very tiny. That way, you don't really have to worry about the fact that the paraxial optics is only approximate. That way, you don't have to worry about the fact that the thin lens equation is only approximate. Other questions?
Do you know what the diameter of these lenses is? Because together, this is a very long lens.
Yes, it is. I don't think he included it in, I got these lecture notes from a pro, and I don't think he included it in his notes. And my guess is that all of the details of this are hidden behind a bunch of non-disclosure agreements. This is a lithographic lens. This is a lens that's used to manufacture computer chips. Somebody spent a whole bunch of money on this lens because they are making many, many things that are even more or collectively more expensive with this lens. So it's worth spending the money on this if you're making chips that you can sell for a bunch of money. It would not be worth spending money on this for a camera if you're working as, say, even the most insane paparazzi would not buy this lens.
So is this like used in wafer production?
Basically, yeah.
Okay.
All right, let's go back. So spherical aberration. Spherical aberration happens even to on-axis objects. Coma aberration. We have repeatedly seen coma aberration. Every time you've had an off-axis object in Zemax and you've seen that little asymmetric shape that looks kind of like a teardrop or a comet, that's coma aberration. Coma aberration happens for off-axis objects, and I will explain in a little bit what it means to say that this aberration happens here and not that one. The basic mechanism of coma is this. Say I've got my off-axis object. Well, I could extrapolate a ray backwards. The ray that's coming from it, as far as the lens is concerned, could just as easily be coming from an on-axis object right here at point A. And so it would do what it always does with spherical aberration. It would deflect this through a larger angle, right? And likewise, it would deflect this other ray, which came in closer through a larger angle. And these two deflections are not symmetric. And the fact that these two deflections are not symmetric is why the image winds up looking asymmetric. We're going to learn in a little bit a design rule that gets pretty close to eliminating coma and certainly minimizes spherical aberration. And those design rules predict something called a shape factor. Again, we'll get to that. What's interesting is that the shape factor that corrects coma is very close to the shape factor that corrects spherical aberration. The reason I'm talking about it now rather than after the more formal definitions is because I want you to see that coma and spherical aberration come from the same mechanism. And so fixing one tends to get pretty close to fixing the other. There's also astigmatism. Astigmatism happens for things that are even, or it's more noticeable for things that are even further off axis. And what it does is instead of, if spherical aberration turns points into circles and coma turns points into teardrops or comets, astigmatism turns points into ellipses. This is the part where the eye doctor says to you, okay, which is more in focus, the vertical lines or the horizontal lines? You know that part of the eye exam? Well, that's where they're checking to see if you have astigmatism, which is just a way of saying that off-axis objects are getting handled asymmetrically. And we already know that off-axis objects can form asymmetric images. We know that from coma. If you get really far off axis, they become even more asymmetric. And if your eye itself is not perfectly symmetric, if it's a little bit deformed horizontally or vertically, yeah, like I see in the comments of football. If your eye has a shape a little bit more like a football, then you have a diagnosable astigmatism. And the correction for that is simply lenses that partially cancel out that effect. Any questions on that?
Professor, I have a question. I know like you're an optics teacher, but when should I be concerned about like astigmatism within my eye? Because I notice I see that like smearing effect often when I see like a tail light of a car. Like if you search up astigmatism on Google Images, you would often see tail lights examples, and I see them like frequently. Should I be concerned?
Okay, so I'll start with the only legally correct answer. When in doubt with your eyes, don't screw around. Go to an eye doctor, let them sort it out. All right? That's the question about what you should do for your own health and safety. If you want to know about the phenomenon, I don't have a good sense of when astigmatism is most common. I mean, this is one of those things that does show up in kids. It's not like some eye diseases that only show up or more frequently show up in old age. When in doubt, you go to an eye doctor and let them sort it out. But as to whether or not you should be concerned, well, I mean, there's levels of concern. There's, I should make an appointment and, sooner, sometime when I get around to it. And there's, I should run to the emergency room, and then there's things in between those. And if you generally are seeing fine, but you just notice that sometimes things are a little bit blurry, that means that if there is something wrong, it's probably early. You should probably go to a doctor, first reasonable chance you get, but you don't need to run to an emergency room and say, I'm going blind. Okay, so that's the only answer I'm comfortable giving, which is that if it's not bothering you too much, get it checked out, but don't say, hey, this is an emergency, fit me in tomorrow. If you notice a rapid change in vision, then you go to an emergency room. Does that make sense?
Yeah, and I also just want to clarify, I'm not under the influence when driving. So from my knowledge, that's how I normally see it, like especially at nighttime too.
Yeah, well, a lot of vision is worse at nighttime because, for starters, when at nighttime you're looking more at point objects. You've got a bunch of dimly illuminated things, and then you've got discrete lights. Whereas during the daylight, everything is brightly lit. So you're going to notice aberrations more cleanly because you're staring at points. I mean, the optometrist rarely says to you, hey, look at this forest scene. The optometrist gives you lines and dots. You know, the optometrist gives you letters, very simple shapes, because they want to diagnose aberrations. Whereas looking at an elaborate scene is not as, it's not as easy to judge, because you've got all these details that could confuse you. And you've got some details that are inherently sharp in the image and some things that are more gradual shading. But at night, when, you know, especially in the modern world with electrical lighting, although even in the past with candles, you know, you see more points of light, and then you can really, aberrations and other eye problems stand out. Now, there's a second reason why some people have problems seeing at night, and that's because sometimes you have worse rods than cones. You might have very good cones and very bad rods. That's a retinal problem. And, you know, I'm not going to tell you, oh, here's what you should worry about, here's what you shouldn't worry about. I'll just say that if your vision seems a little weird, go to a doctor. If it's changing rapidly, go to an ER. That's the basic rule. Sudden changes, you never know what's going to happen, go to an ER. Okay, anything other than asking a PhD to do an MD's job? I mean, I like talking about the science of the eye, but as soon as it goes from, I find this effect interesting, or how does this organ work, to, should I be concerned about my vision? I mean, I'm not about to open myself up to a lawsuit. Okay, so astigmatism. It comes from malformation. I think Justin's football analogy is a good one. Here's an extreme example of astigmatism. One very clever thing that people do in biomedical optics is they routinely say, hey, that's not a bug, that's a feature. So if we think about it, it's hard, it's very easy in an image to figure out where something is left, right, up, down. But the amount of defocus can be hard. Now, of course, if something is really, really far away from the plane that it's supposed to be, and something really, really out of focus, well, of course you notice that. But what if you're looking under a microscope and something is only defocused by 200 nanometers? 200 nanometers is nothing. The lens itself is not normally, good lens will not normally be able to tell the difference between something that's 200 nanometers out of focus and something in focus. So what some people did is they said, well, let's break the lens. No, not with a baseball bat. Let's put a cheap cylindrical lens in the beam path. Let's take a lens that has absolutely no business being there. A lens that the manufacturers did not account for when they had a whole team of people design this, microscope objective, which probably has several lenses in a row. And let's deliberately introduce some astigmatism. Now, here's the beauty of it. The astigmatism depends on how far in or out of focus the light is, okay? And so because it depends on how far in or out of focus the light is, you can actually see the effect. And if it's out of focus, if it's too close to the lens, you get one effect, you get one orientation. And if it's too far from the lens, you get the other orientation. So you get this elliptical image. How elliptical it is tells you how far away from focus it is, and how the ellipse is oriented tells you whether it's too close or too far. And I just think this is endlessly clever. Of all the techniques that people have used to do these high precision measurements, this remains one of the top two competitors. The best, I think, there is a group that has come up with something that involves these really elaborate phase masks and diffraction patterns and these really cool helical patterns that the thing gets distorted. It produces a distorted image where the point object makes this helical image instead of just a little point. And the helix rotates. The further in or out of focus you go, the more the helix rotates. It's really cool. It's also more expensive than taking a cheap cylindrical lens and dumping it in the beam path. And it requires more elaborate image analysis. Any questions? Let's put it this way. I could write a subroutine to analyze these images in less than an hour. I couldn't write the whole software package, but I could write the extra subroutine just to decode this information in less than an hour. The subroutine to decode the double helix, I need more than an hour just to think about how to decode that. Any questions? There are other aberrations, distortion. Again, these aberrations I'm bringing in each aberration becomes more important as you go further off axis. Distortion you notice with magnifying glasses. And then there's field curvature. And field curvature is basically when the image plane itself is curved. And that's most noticeable for things further off axis. And this is the Kepler Space Telescope sensor array, where they actually deliberately designed for field curvature. They said, all right, they optimized a bunch of other things. Eliminating field curvature would have required doing even more. So they just said, screw it. We'll make a curved detector. We'll just accept that our image plane is going to be curved, and we'll make a curved detector. And that's what they did. Any questions?